Exercise 1.1. What is the force between two small charge sphere having charges 2 into 10 raised to minus 7 and 3 into 10 raised to minus 7 placed 30 centimeter apart? So here we have two small charges which are separated by 30 centimeter. The magnitude of one of the charge is 2 into 10 raised to minus 7 and another charge is 3 into 10 raised to minus 7. So it is asked what is the force between them. So as they are charges, they will exert Coulomb's force of electrostatic or Coulomb's electrostatic force, and as they both are positive, so there will be a force of repulsion between them. To solve this question, we can use Coulomb's equation directly, which can be given as F is equals to K Q1 Q2 by R square, where K is a Coulomb's constant, Q1 is the magnitude of one of the charge and Q2 is the magnitude of another charge, and R is the distance between them. Here R is in centimeter, we have to convert that into meter. So it is 30 into 10 raised to minus 2 meter, which can be rewritten as 3 into 10 raised to minus 1. On solving this, if you put all the values, then what you will get here 9. So here it is 9, 2 and 3. So 2 and 3. Here 10 raised to 9. Here 9, power is negative, so it is minus 7, so minus 7, minus 7, and it is 10 raised to minus 1 into 2, so it is 10 raised to minus 2. This goes up, so it becomes plus. So this 9 and 9 will get cancelled because square of 3 is 9. On solving this, we will get 6 into 10 raised to minus 3 Newton and repulsive force. Why repulsive? Because both the charges are of similar type, that is either both are positive or both are negative. So here both are positive. Question number 1.2. The electrostatic force on a small sphere of charge, here it is given 0.4 microcoulomb, due to another small sphere of charge 0.8 minus 0.8 microcoulomb. So whenever there is a negative sign is given or positive sign is given, the sign indicates whether the forces will be attractive or repulsive. Suppose if two charges are positive or both are negative, so same charge is repel, so there will be repulsion. Here one is positive, another is negative, so there will be force of attraction. The force is given and it is asked that what is the distance. So again we can use Coulomb's equation. In Coulomb's law, what we know about Coulomb's law? We know that F is equals to K Q1 Q2 by R square. What we want? R, we want distance. So R square is equals to K Q1 Q2 by F. So what we will do? We will just rearrange the equation. So we have rearranged. So we have made here R as a subject. So here you can see R square is equals to K Q1 Q2 by force on 1 by 2, and here K is given 9, K is 9 into 10 raised to 9, value of one charge is 0.4 into 10 raised to minus 6 coulomb, 0.4 microcoulomb, that can be rewritten as 4 into 10 raised to minus 7. Similarly, the value of other charge is 0.8 into 10 raised to minus 6, so I can write 8 into 10 raised to minus 7. See, here I am not considering sign, right? I have not written negative sign because I am considering only its magnitude. The sign just to show whether the force is attractive or repulsive, that's why we are not considering sign here. So here on solving, here you can see that here 9, then here it is 4 and here it is 8. So 9, 4, 8. Then about power, it is 10 raised to 9, 10 raised to minus 7, so minus 7, minus 7, minus 7, and here it is 0.2 Newton. So 0.2 can be written as 2 into 10 raised to minus 1. It will go up, then it will become plus 1, right? So here 2 2s. Now with what we are remaining here, you can see here it is we are remaining with 9, 2 and 8. So 8 2s 16, and here you can see there is a square, so we can put root on both the side. So here root of 9 is 3, and root of 16, because 8 2s are 16, it is 4. So 3 4s are 12, and here power is 10 raised to minus 4. So root of 10 raised to minus 4 is 10 raised to minus 2. So it is 12 into 10 raised to minus 2 is our final answer, which is in meter. So 10 raised to minus 2 meter is centimeter. So it is 12 centimeter. In the part B of the question, it is asked that what is the force on the second sphere due to the first. Here it follows Newton's second law, right? So force on both the charges are equal and opposite, equal in magnitude and opposite in direction. So force on 1 by 2 is equals to negative of force on 2 by 1. So it will be 0.2 Newton, only magnitude, right? If we consider direction, then it will be minus 0.2. Then next, here it is question number 1.3. We have to check, it is given that check the ratio Ke square by GMEMP is dimensionless. Look up the table of a physical constant and determine the value of this ratio. This question is actually from the example. If you check maybe 1.2 or 1.3 example, right, or 1.4, same kind of question is given, and it is asked that find the ratio of the the electrostatic force to the gravitational force, right? So same question is there. Here you can see that in the first part, here it is Ke square. If I divide this term by r square, one more term is there, it is GMEMP. If I divide this term also by r square, we will get the same term again. Now what is this Ke square by r square? It looks like Coulomb's equation. So Coulomb's equation, so we can say it's a Coulomb's force, electrostatic force. And this looks like gravitational equation, force of gravitation or gravitational force between the two masses. So it is divided by F gravity. Now as is the ratio of two forces, then its dimension will be m0, l0, t0. So here I have written these are two forces. So both forces, either it's a gravitational or electrostatic or nuclear, all forces have same unit, and that is Newton. So their dimensional formula will be same, m1 l1 t minus 2. Here m1 l1 t minus 2. So this will get cancelled and you will get m0 l0 t0. Yes, this ratio is dimensionless. Now which is the another method you can use? You need to see, if you try with the another method, then you have to put the dimension of Coulomb's constant, charge, gravitational constant, then mass of proton, that is mass, and here also mass. So you have to put the dimensions of all this quantity, and then you have to obtain m0 l0 t0. So this method that I have done is more better than other methods, so it will be easy for you to do the calculation. Now in the second part of the question, it is asked that what does the ratio signifies, right? We have to find the value of the ratio, and then we have to say that how what this value the ratio signifies. So what I have done, I have just put the values. Here you can see Ke square. So here it is K, the value of K is 9 into 10 raised to 9. So that is K. Then here it is here E square. So value of E is 1.6 10 raised to minus 19. So it is E square. Here you can see the value of G 6.67 10 raised to minus 11. It's a gravitational constant. Then mass of electron 9.1 10 raised to minus 31, and mass of proton 1.67 10 raised to minus 27. Now what I have done, I have just put all the powers together and all the numbers together. So here 9, so here 9, then 1.6, here it is square, so 2 times 1.6 1.6, then it is 9, and here 19 into 2, it is minus 19 into 2, it is minus 38. So 9 minus 38, and on the denominator side you can see that 6.67 9.1 and 1.67, 9.1 and 1.67. Now all the powers, minus 11, minus 11, minus 31, minus 31, minus 27, minus 27, right. So I have just done a very simple calculation here. Now on multiplying all these three numbers, you will get this value, and multiplying all these three numbers, you will get this value, right. And here 9 minus 38 is minus 29, and minus 11 minus 31 minus 27 is minus 69. This minus 69 will go up, it become plus 69. So here it is plus 69, it is plus 69 minus 29. So the difference will be 40. So if you again divide this two number, you will get 0.227, and the power is 10 raised to 40. What I am doing here is just removing 110 from this, so it becomes 2.27 into 10 raised to 39. So this is the value of the ratio. Now it is asked, what does this value signifies? Here you can see that the ratio is actually Fe by Fg, that is electrostatic force to the gravitational force between a electron and a proton. So here we can see that the electrostatic force is 10 raised to 39 times that of the gravitational force. That is, if you place one electron and one proton, if you place one electron and one proton at distance r, then the electrostatic force will be nearly 10 raised to 39 times stronger than the gravitational force. That is, electrostatic force is very large than the gravitational force. This is what the ratio signifies. So I hope you are clear with this question. If you have any doubt or query, you can just ask in the comment. I will make another video. Okay. Now moving to the next question. Here question number 1.4. Explain the meaning of statement electric charge of a body is quantized. So let us go with the first one. So it is said that, see, let us assume I have one body. Let us assume here I have one object and I want to charge this body, right, just by transferring electron. So how much charge I can put on this body? How much charge I can put on this body? I can put either equal to E, then I can add one more electron, then I can add one more electron. That is, every time I am adding charge equal to electron, that is 1.6 10 raised to minus 19, then in the next case I am adding plus 1.6 into 10 raised to minus 19. So the charge on a body will always increase in multiples of E. So on a body here the charge is 3E. Maybe if I supply one more electron, right, then it becomes plus 1, so it becomes 4E. That is, the charge on a body always increases or decreases in the multiple of E. You cannot add fraction of electron, right. We are not talking about quarks. Okay, quarks, the protons and neutrons actually are made up of quarks, but they are never seen separately, means they are not fundamental, right, and that you will learn in higher classes. So for you now the fundamental particle is electron. That is for a unit about charge. When we talk about charge, the fundamental particle is a electron, right. So here only the integral number or integers, the electron can be either 1 or 2 or 3. If you talk the number of electrons on a body, it always in the integers, it never be in fraction, right. So here only the integer or integral number of electrons can be transferred from one body to the another, and not in fraction. We cannot transfer electron in fractions. Hence a body can possess total charge only in the integral or integer multiple of fundamental unit charge. That is, the charge on a body will always Q equals to Ne, where N is an integer, that is N is equals to either 1, 2, 3, 4. It can never be a decimal or a fraction. So where Q is the total charge on a body, N is the number of electrons, and E is the charge of one electron, right. So this is the quantization, right. Quantized, see, if we talk about quantization, the meaning of quantization is something exists in fixed numbers or fixed packets. Okay, I don't want to go into the depth because this is not a theory lecture, right? But once if I will make theory lecture, then in theory lecture we will discuss in detail. Now next one is a B part. In the B part, why can one ignore quantization of electric charge when dealing with macroscopic levels? That is, if we deal with large number of particles or at a very large level, then we can ignore quantization. That what it is asked here, why we can ignore. See, a very simple example. Let's say you are going to buy some let's say wheat flour, गेहूं का आटा लेने आप जा रहे हो, राइट, और गेहूं के आटे में से एक दाना गिर गया, एक छोटा सा तिनका गिर गया, क्या उससे कुछ फ़र्क पड़ता है? नहीं पड़ता है, राइट, क्योंकि जो दाना है उसके मुकाबले जो पूरा कंटेनर है गेहूं का वो बड़ा है, उसमें इतने दाने हैं कि आप एक दाने को इग्नोर कर सकते हो. बट इफ़ वी आर गोइंग टू बाय लेट्स से डायमंड्स, then a very small, and these diamonds are let's say very expensive, then if a very small part of let's say diamond, right, let's say you have 100 diamond, if one of the diamond fall off, then you will be in tragedy, right? So at that time we cannot ignore, right, a single diamond, right? But when we talk about wheat flour, गेहूं के आटे की बात करते हैं, तो वहाँ हम एक दाने को इग्नोर कर सकते हैं, उसका जो एक दाना है उसको इग्नोर कर सकते हैं. So at that time we are not interested in that a single term. So here also when we talk about charges at very large magnitude, let's say I am talking about a charge of, let's say it's not very large, it's not very small, 1 microcoulomb. So 1 microcoulomb contain approximately 6.25, you can calculate this, Q equals to Ne, make N as a subject. So 1 microcoulomb contains 6.25 into 10 raised to 12 electrons, right, that is nearly 10 raised to 13 electron. So 10 raised to 13 electron is a very large number. If one electron falls off that part, we can ignore, right? So the same thing is asked here, because the magnitude of electron or magnitude of charges used at macroscopic level, that is at a high level, at a large level, is very huge. Suppose if I talk about 1 coulomb, then 1 coulomb include 6.25 into 10 raised to 18 electron, which are very large numbers. So at this stage we can ignore if one or two electrons are not there in this counted number, counted electrons, right? So we can ignore. So because the magnitude of the charges used at macroscopic level is very large as compared to charge of 1 electron, we can ignore quantization, right? Now one more thing we can add into this, that is here you can see that I have added one point from the NCERT. In this respect, the grainy nature of the charges is lost and it appears to be continuous. That is, when we say how the charge on a body increases or decreases, so it increases or decreases in steps. If we talk about micro level, not macro level, micro, very small, let's say we talk about nano level, right, which is smaller than the micro level, then the charge on a body increases like this, that is it is either E or 2E, 3E, 4E. But if we talk at very large level, right, then this appears continuous. Let me explain you with an example, right. Let's say this is what I am drawing like this. So what you see here, you see steps, right, but if I zoom out, let's say again if we zoom out, if we zoom out, right, then it will appear like a straight line. The best example is, let's say there is a mountain, right, when you go out and you observe mountain, so you observe straight lines, but if you go very close you will find that these are not straight lines, right, इसमें ये straight नहीं है, इसमें कहीं सारे गड्ढे हैं, right. So there are, you can see there is a valleys and mountains, small valleys and mountains, right. This is not a straight line. So at a very large distance you can see a straight line. So similarly, at a very large level or macroscopic, not micro, macroscopic level, the charge on a body appears not in steps, that is not in grainy natures, but it appears to be continuous like this mountain, okay. So okay, Now question number 1.5. When a glass rod is rubbed with a silk cloth, charges appear on both, right? For example, I have this silk cloth and let us say this is a glass rod, and now I am rubbing this. What will happen? The silk cloth, let us say, see, we are not going into the which acquire positive, which acquire negative, right? So let us assume the silk acquires negative. So what will happen? The same amount of electrons and the same amount of positive charge will acquire by the glass, because the electrons are moving from glass to silk, right? So it is asked that both acquire charges. Then a similar phenomena is observed when many other pairs of bodies, right, when they rub. For example, if you rub wool with a glass, right, or if you rub wool with ebonite or amber, the same thing we observe. Explain how this observation is consistent with the law of conservation of charge. Now what is law of conservation of charge? Charge can neither be created nor be destroyed, right? So here we have to explain that although the charges are transferring from one body to another body, there is no destruction of charge, the charge is conserved, okay? So that we have to justify. So here what is given? Before rubbing, both glass rod and the silk cloth are electrically neutral. It is not always, but this time they are neutral. In other words, the net charge on the glass rod and the silk cloth is 0. Yes, in first case, initially both are separated, they were not rubbed, so the net charge was 0. Now when we rub, so when the glass rod is rubbed with a silk cloth, few electrons from the glass rod get transferred to the silk cloth. So what is happening here? Let us say this is a glass rod and this is a silk cloth. So electrons are transferring from glass to silk. So here as a result, the glass rod becomes positive charge and the silk cloth negatively charged. Since the magnitude of positive charge on the glass rod is same as that of negative charge on the silk, right, means whatever amount of charge transferred to silk, the same charge but the opposite appears on this glass rod. The net charge on the system is 0 because the equal amount of charge appears on both the objects, so that is, it is 0. Thus the appearances of charges on the glass rod and the silk cloth is in accordance with the law of conservation of charges, that is, here no new charges are created, right, that is why it follows law of conservation of charge. Question 1.6. 4-point charges 2 microcoulomb, minus 5 microcoulomb, again 2 microcoulomb, minus 5 microcoulomb are located at the corners of a square ABCD. ABCD mostly give names in anti-clockwise manner when it is not given. So I have given in anti-clockwise manner. Then here the side of the square is 10 centimeter. So let us assume this is 10 centimeter. What is the force on 1 microcoulomb placed at the center? So here you can see there is 1 microcoulomb charge is placed. You can carefully observe this, right, and then we will solve, right. So here you can see there is a square whose side is of 10 centimeter and there are 4 vertices, and on each vertices or at each corner there is a charge which is labeled in the figure. Now here there is one positive charge, right, here you can see plus 1 microcoulomb which is placed at the center. Now what will be the force on this 1 microcoulomb, positive 1 microcoulomb charge by this? See, this is also 2 microcoulomb and which is positive. So positive repel. So this positive charge at corner A will repel this charge in this direction here. So it repels in this direction, which is labeled here. So force on 1 microcoulomb charge placed at the center is Fa. So here the direction Fa is labeled, right. Similarly, this charge of 2 microcoulomb placed at corner C is also positive. So, positive positive repel. So, it will exert force this 1 microcoulomb charge in this direction, right. So, it is FC. So, here you can see FA and FC are in opposite direction, that is the angle between them is 180. So, the net force along this line can be calculated by FA minus FC, that we will see later. Right now just I am explaining. Now, if we talk about this charge at B which is negative and the charge at this center 1 microcoulomb is positive. So, what will happen? It will pull this negative charge minus 5 microcoulomb will pull 1 microcoulomb towards it, okay, because it will attract. One is negative, one is positive. Similarly, the charge at corner D is also negative, minus 5 microcoulomb. So, it will also pull this charge in this direction because it is negative. So, negative attracts positive, okay. So, this is the picture that you can see here. Now, let us put it mathematically. So, here when we want to use Coulomb's law, right. So, what is the Coulomb's law? F is equals to K Q1 Q2 by R square, where R is the distance between the two charges. So, in all the cases here there is a and here we have 1 microcoulomb. So, the distance is half of the diagonal. Similarly, if we talk about B and O, then the force applied by B on O, that is on 1 microcoulomb, is towards B, and the distance, the R, is also half of this diagonal. So, in all these 4 cases the R become half of the diagonal. So, we have to find the length of the diagonal, then we have to divide by 2. So, here we have square whose length is L. So, you can use Pythagoras theorem and you can obtain this hypotenuse, right. So, this is we can use Pythagoras theorem and we can obtain hypotenuse. So, this hypotenuse is actually the diagonal of the square and we want R, that is we want this length, half length. So, this is if this is L, right, the sides are L, then using the hypotenuse, using the Pythagoras theorem, we can obtain this diagonal to be root 2L, right. It is simple, L square plus L square under root, right. I am using a very simple maths, right, there is no rocket science, you can understand this. So, the half of the, so what we can get is this is root 2L. So, what will be the half of this? This half I want. So, it is root 2L by 2, right, because we need to divide it by 2. Now, it is root 2L and 2 I can write as root 2 into root 2. Root 2 into root 2 is 2. So, root 2 cancel. So, the length of the diagonal will be L by root 2, half of the diagonal. The length of half of the diagonal is L by root 2. So, here I have explained this. L, that is the side length is 10 centimeter, diagonal is root 2L. Now, we want this AO, then we want BO, then we want CO and DO. So, AO, BO, CO and DO, they are half of the diagonal, and half of the diagonal we have obtained as L by root 2. And what is L? It is 10 centimeter. So, as it is 10 centimeter, so we can write it as 10 by root 2, and again if you solve this, it is 5 into 2 by root 2. Again you can solve this and you will get 5 root 2. So, the length of the diagonal is half of the diagonal, that is AO, BO, CO and DO is 5 root 2 centimeter, right. It is not a lengthy question, but what I am explaining is lengthy. I am going into the depth. So, those students who are bad at maths can understand this. Now, next is, now I want to find the force exerted by the charge A, force exerted by charge A on this charge, and they will repel, right, because both are positive. So, what is the Coulomb's equation? K Q1 Q2 by R square. So, here you can see force applied by A on Q naught is equals to K QA Q naught, that is the Q naught I am writing because Q, the charge which is at the center, it is divided by AO square, where AO is our R. So, I am just putting the value. So k is 9 into 10 raised to 9. QA, the charge at A is 2 into 10 raised to minus 6. The charge at the center here is 10 raised to minus 6, that is 1 microcoulomb, and AO is 5 root 2 into 10 raised to minus 2 square. So this become 3.6 Newton. You can see the direction of the force. What is the direction of the force? The direction of force is labeled here, which is FA, and it is along O to C, right? So the direction of the force is OC. Similarly, you can check for force by C, it is K, Q, C, Q naught. Now I am not going in depth, right? Now you can understand this. So I have just put all the values here. Q, it is value of 9, then QC, it is 2 microcoulomb, then 1 microcoulomb, then again and the distance R, and again we are getting the value 3.6. And as again C and the charge at center both are positive, they will repel. So here you can see that it is along OA. So OA and OC are opposite in direction, right? So these forces are equal and opposite in direction. So their summation will be 0, right? So this force, the summation of these two force F and FC is 0. Now let us talk about the force on charge at O due to charge at B and charge at D. So the force on charge at O due to charge at B is FB is equals to K QB QO by BO square. Again I am just putting the value of K, value of charge at B, and value of charge at center, again value of R, that is OB. So if you calculate, you will get 9 Newton. Similarly, right, you can calculate the force exerted by this charge D on the charge at center, again you will get 9 Newton. Now if we trace their direction, then these two charges, right, which is given in the question, the charges at B and the charge at D, both are negative, so they will pull. So FD is along OD and FB, force by B, is along OB. So both are again equal and opposite, so they cancel each other and the net force will be 0. Now what is the total force? So the total force is the addition of all the forces. So if I add these two force, FA, then FC, then FB and FD, so I will get 0, because FA and FC is 0 and FB and FD, their vector sum is 0. Okay, so I hope you are very clear with this one. Number 1.7. A. An electrostatic field is a continuous curve that is a field line cannot have sudden breaks. Why not? That is, see, when we are drawing electric field lines, we draw electric field lines like straight lines, right? Or we draw like curved lines. We are not drawing electric field lines like curved line. We are not drawing like this, right? So this is a wrong representation of electric field lines. Why this is a wrong representation of electric field lines? That it is asked. So see, let us assume I am placing a charge. Let me use a proper pen. Let us assume here I have a charge. This is a field line. Let us assume if I place a charge here at this place, let us assume I am placing a charge here, then what will happen? This charge will experience force. The charge will experience force, and it will be, if it is a positive, it will experience force in the direction of this field, right? And it will move in a continuous manner. Either it will move with a constant velocity or it will be under a uniform acceleration depending upon the field, right? Now suppose if the field has breaks like this, like let us assume this red lines are field which represent field. Let us assume it is wrong, but let us assume it is a field. Then in this case, if I place a charge here, then the charge will experience force. Then in this region what will happen? Nothing, right? Because there is nothing. I have drawn nothing, means there is no field. So either the charge will jump or the charge will stay at this position only. But in real case, the charge will not jump. That is, the charge will move continuously. The charge move continuous only if there is a continuous field, right? So what we can write? A charge placed in electric field experiences a continuous force. The field line cannot have sudden breaks because the charge moves continuously and does not jump from one point to another. The B part, explain why two field lines can never cross each other. We know that electric field line is a vector quantity. So, how we add vectors? Let us assume I have one vector here which is pointing in this direction, and I have another vector which is pointing in this direction, and this is the angle between them. So, what will happen? We will produce the resultant by considering the angle and the magnitude. This is vector A, this is vector B. So, how we will obtain its magnitude? So, it is A square plus B square plus 2AB cos theta. That is how we obtain their magnitude. And by using the parallelogram method, we obtain its resultant, right? Means the resultant will have only one direction. Similarly, if I place a charge at this position, let us assume I am placing charge here, then either charge can go in this direction or the charge can go in this direction. That is, a charge can experience force only in one direction. That is, if there are two fields present, then the charge will experience force in the resultant of that field. That is, there will be only one direction is possible, no two direction. That is why two lines are not possible at one point, because if they cross each other, there will be two directions of E, which is not possible. Why it is not possible? E is a vector quantity. So, if two lines cross each other, the resultant field will only point in one direction. That is why there is only one direction. See, the field line crosses, but when they cross, they produce a resultant line. So, we can see, or we can show only the resultant line, not the two line. Question number 1.8. 2 point charges 3 microcoulomb and minus 3 microcoulomb located 20 centimeter apart in vacuum. So, here I have shown you here, you can see here I have 3 microcoulomb, here I have minus 3 microcoulomb, which are located 20 centimeter apart. So, from their center, this charge, A charge is located 10 centimeter, which I can write 0.1 meter, and another charge is located again at 10 centimeter from this center. So, it is 0.1 meter. Now, what is asked to find? In this question, it is asked to find that what is the electric field at midpoint O of the line joining the two charges. So, this is the line which joins the two charge, and we have to find the force at the midpoint of these two, means at the point O. See, here A is positive. So, from A, the field line always away from it, right? Whereas the charge B is negative. So, the electric field lines always comes towards the negative charge. See, if there is a positive charge, the field lines move away from it, and if there is a negative charge, the field line falls on it or terminate on it, or it is towards the center of negative charge. So, here the field produced by charge A is from A to O, that is, it is towards B, and the field produced by this B, which is negative, is also towards this, towards right side. So, both are in the same direction, so we can add this field directly. So, the resultant field at O is the summation of the field due to positive charge plus the field due to negative charge, because it is in the same direction. So, field at A or field at O is equals to electric field due to positive charge plus electric field due to negative charge. Now, what is the equation for electric field? It is kq by r square. So, here we have k, the charge q, and r1 square, which is the distance. The value of k is 9 into 10 raised to 9, charge is 3 microcoulomb, and the distance is 0.1 meter, that is 10 raised to minus 1 meter, and its square. If you solve this, you will get this answer, 27 into 10 raised to 5 Newton per coulomb, which is pointing along O to B. You can see this in figure. Now, what about the field produced by the negative charge? The field produced by negative charge is again kq by r square. So, kq by r square. Here I am not considering negative sign. See, I am just finding their magnitudes, right? Because negative sign gives us this direction. We have already obtained the direction. This charge is negative, that's why the field is directed towards right. Similarly, this is positive, so field is directed towards right. So, the angle between the two vector is 0. So, we can directly add them. When the angle is 0, we can add them. So, again the magnitude is same as the previous one, 27 into 10 raised to 5, and is also along OB. So, we are directly adding these two vectors. So, it is 27 into 10 raised to 5 plus 27 into 10 raised to 5. It is 54 into 10 raised to 5, which is also pointing along OB. Now, in the second question, it is asked that if a negative test charge of magnitude 1.5 nanocoulomb is placed at this point, what is the force experience? Now, we know that if there is a electric field, and in this electric field if you place a charge q, then you will experience force F is equals to q into E. So, the field at this point, already I have drawn here, the field at this point that we have obtained is 54 into 10 raised to, maybe it was 5, it is 5 Newton per coulomb. It is in this direction, right? Now, if I place a charge, if it is a negative charge, it will experience force towards left side, right? Because negative charge experiences force in the opposite direction of the electric field. So, the charge is 1.5 nanocoulomb and the electric field is 54 into 10 raised to 5. If you multiply, you will get 81 into 10 raised to minus 4, which is along O to A. O to A means it is towards left side. Here it is A, here it is O. 1.9. A system has two charges, QA 2.5 into 10 raised to minus 7 and minus 2.5 into 10 raised to minus 7 located at, so their positions are given 0 0 minus 15 and 0 0 plus 15. What is the total charge and the electric dipole moment? Now, if this is our whole system, then the total charge of the system is Q is equals to Q1 plus Q2. Here we have one negative charge and one positive charge. So, if we add them, the summation will be 0. So, QA plus QB, their summation is 0. So, the net charge of the system is 0. Now, in the second part of the question, it is asked that what is the dipole moment. Now, how we can find the dipole moment? We know that dipole moment is equals to separation between the charges and the magnitude of one charge. Now, it is given here QA is located at 0 0 minus 15. So, how I have drawn here, I have put x direction like this. So, here I have label, it is x, which is coming out of this mobile device or from which you are watching. It is coming out of the plane of this device, right, x, and the z is going towards right and y is going up. Okay, so this how this coordinates I have drawn. It's our choice, right, how we draw, but all three should be perpendicular. Now, here, so the charges are, you can see here, they are along the y line, z line, right, they are along the z axis. So, from the center, the positive charge is located at distance minus 15. So, here it is minus 15 centimeter, and similarly negative charge is located from the center towards right plus 15 centimeter. So, the separation between the charge is 15 plus 15, which is 30 centimeter, and the magnitude of one charge is minus 2.5 into 10 raised to minus 7 coulomb. So, if you multiply, you will get 75 into 10 raised to minus 19 coulomb meter, which is the SI unit of dipole moment. Question number 1.10. An electric dipole with dipole moment 4 into 10 raised to minus 9, that is 4 nanocoulomb meter, or simply we can say 4 into 10 raised to minus 9 coulomb meter, which is aligned 30 degree with the direction of the uniform electric field of magnitude 5 into 10 raised to 4. So, the electric field here, it has magnitude 5 into 10 raised to 4 Newton per coulomb. Calculate the magnitude of the torque acting on it. So we have to find the magnitude of torque. So we have expression torque is equals to Pe sine theta, where P is the dipole moment. So dipole moment is 4 into 10 raised to minus 9, electric field is 5 into 10 raised to 4, and sine 30. Here the angle between the dipole moment and the electric field is 30 degree. Dipole moment is negative to positive. Right, so 4 5s are here 20, 20 by 2 is 10, and minus 9 plus 4 is minus 5. So it is 10 raised to minus 4 Newton meter. Is question number 1.11. A polythene piece is rubbed with a wool is found to have a charge negative charge of 3 into 10 raised to minus 7 coulomb. Now see, the polythene acquires negative charge. Okay, means here what is happening, if you rub a piece of, here it is given rub with a wool, so you are rubbing with a wool is rubbed with a, let's say, polythene. So the polythene acquires negative charge, it means it attracts electron from the wool. So a mass is getting transferred from wool to polythene, right? Because see, proton cannot move, they are inside the nucleus. So here the electron can move from one material to another material. It is asked that estimate the number of electrons transferred from which to which. So here the charge acquired by the polythene is given minus 3 into 10 raised to minus 7, right? So negative charge means the polythene has acquired electron. So we have equation Q equals to Ne for a charge on a body. So N is equals to Q upon E, where N is the number of electron, Q is the charge, and E is the charge of one electron. So the charge transfer is given here 3 into 10 raised to minus 7. I am considering here magnitude because I want number, and the charge of one electron is 1.6 into 10 raised to minus 19. If you solve this, you will get 1.875 into 10 raised to 12, means this many number of electrons are transferred from wool to polythene. It is asked that is the transfer of mass? Of course yes, because the electrons are moving from wool to polythene, means the wool is acquiring electron, so it becomes negative charge. So yes, wool loses 1.75 into 10 raised to 12 electrons, because the same number of electrons are acquired by this polythene, and hence mass equals to, now see, the mass of one electron is 9.11 10 raised to minus 31 kg, or 9.1 into 10 raised to minus 31 kg. So one electron carries this much mass. So the total mass transferred is number of electron into mass of one electron. So this is the formula I have used here. If you multiply, you will get 1.706 into 10 raised to minus 18 kg. So this amount of mass is transferred from wool to polythene. Question number 1.12. Two insulated charge sphere A and B have their centers separated by distance of 50 centimeter, which I have shown here. You can see here charge A, here charge B, which are separated by 50 centimeter, that is 0.5 meter. What is the mutual force of electrostatic repulsion if the charge on each, so it is again related to Coulomb's law, right? So we have to find the charge, the force between them. The radius of A and B are negligible, right? So that is not important right now. Okay, so what is Coulomb's law? F is equals to K Q1 Q2 by R square. So it is KQ because both charges are equal, which is given. So it is KQ square by R square. The value of K is 9 into 10 raised to 9. What is the value of K? 9 into 10 raised to 9. What is the value of Q? Charge Q, it is 6.5 into 10 raised to minus 7. Both are equal. So it is 6.5 into 10 raised to minus 7 square. And the separation is 0.5 meters, so it is 0.5 square. Now if you solve this, right, what answer you will get? How you will solve this? Either you can use calculator or you can solve by yourself. It is 9 into 10 raised to 9, then here you have 6.5. So 6.5 into 6.5, then here it is minus 7. So minus 7 into 2, so 10 raised to minus 14, and here it is 0.5 square, so it is 0.25. You can solve this, you will get this answer 1521. into 10 raised to 9 minus 14. So your final answer will be 1521 into 10 raised to minus 5, or you can write, if you shift 3 zeros from here, right, then it is 1.521 into 10 raised to minus 2, right, it is 1.521 into 10 raised to minus 2 Newton. Now in the second part of the question, it is asked that what is the force of repulsion if each sphere is charged double? Means, if let us assume the first sphere has charge q and second has also q. Now both the sphere charge double, right? So our new q1 will be 2q, q2 will also be 2q, and it is also asked that the distance between them is half. So r dash, the new distance, become half. So let us assume, right, now we are using Coulomb's law. So F dash new force is equals to K, then it is Q1 dash, it is Q2 dash, right. So K is equals to 2Q into 2Q, right, divided by R by 2 square. So 2 into 2, it is 4, here R by 2 square is R square by 4, 4 will go up. So again it is 16 KQ square by R square, so 16 times of the original force. So the new force will be 16 times of the original one. So original force that we have obtained is 1.521 into 10 raised to minus 2. So 16 into 1.521 into 10 raised to minus 2 is 0.243 Newton. Now question number 1.13. Figure 1.3 shows tracks of 3 charged particles in a uniform electrostatic field. Give the sign of 3 charges. Which particle has the highest charge to mass ratio? So first we will solve first part, where it is asked give the sign of the particle. Let me zoom here. What you can see here, there is an electric field which is pointing from positive to negative, right? The electric field always point from positive to negative. So this is the electric field, right? Now when you have a charge, let's say I have a positive charge and a positive charge is put here, then what will happen here? Then this positive charge will experience force in the direction of the field. If I place negative charge, then negative charge will experience force in the opposite direction of the field. Means here you can see that the charge following this track is going towards the upper plate, towards the positive charge, means this is negative. Similarly, this is also going towards the upper plate, this is also negative. So the charges which are going upward, which are 1 and 2, are negative, and the third charge is going towards negative plate, so hence it is a positive. So I have written here, you can copy this one. Positive charge experience force in the direction of electric field and negative charge experience force opposite to E. Therefore 1 and 2 are negative and 3 is positive. Now in the second part of the question, which particle has highest charge to mass ratio, it is asked. Now to find this one, what we are doing is, see, you are very familiar with projectile. That is, when you throw a ball, right, in the gravitational field from some building, then what will happen? This particle, let's say if I am throwing one particle in forward direction, so the particle will fall like this. Why? Because it is under two motion. One is uniformly accelerated gravitational and another is uniform motion. So if there was no gravity, then the particle will move in a straight line. So the horizontal motion is a straight line which is with uniform velocity, whereas the vertical motion is under the influence of gravitational force, right? So this velocity in the vertical direction increases continuously, right, and that's why it is falling like this. Your 11 should be clear, right? Then you can understand this one. Now, so I have drawn here, you can see there is one positive charge particle, right? You can assume negative also, right, but positive is convenient for me. So I have thrown positive in the forward direction, so the motion in the forward direction is uniform motion. So for uniform motion, let us assume the velocity is Vx in the horizontal direction. So the distance covered, let us assume the length of this track is L or X, whatever you want to assume, right? So the distance covered in X by time t. So how much time it will take to reach the other part? So time is equals to x by Vx. Now in that time the particle will move, right, here it is given here. In that time the particle will get deflected, because when it leave this place, now there is no electrostatic force which deflect. So till the time they cross this x distance or the length of the plate, how much they are deflected, right, that we are finding. And why we are finding that you will get to know very soon. But here the direction, the force, the electrostatic force is acting towards downside, right. So the electrostatic force F is given by equation Q into E, right. Here electric field is uniform, charge is also Q, which is also uniform. So here the force is uniform, and for that we can use Newton's law, F is equals to ma. So the acceleration in this is A is equals to QE by m, right. So due to this acceleration, its velocity in the vertical direction increases continuously. So we are using this fact to solve our next part of the question. So here the horizontal motion, right, that we have already discussed. Now vertical motion is uniformly accelerated due to the electric field. So we can write the equation for acceleration as A is equals to QE by m. Now for uniformly accelerated motion, we have one equation. See, these are traveling the same distance with the same velocity in the forward direction. So they all are moving together in the forward direction with the same velocity. What is the difference here? The deflection. See, if I draw a straight line here, you can see this particle deflected by some angle, this particle also deflected by some angle, and this particle also deflected by some angle in the y direction, right. So one of the particle is deflected more, whereas other two particles deflected smaller. So why they are deflected? Because of their charge and mass, right. So that's why we are using this equation, second equation of motion. So we have second equation of motion, y is equals to ut plus half at square, and we are using only for vertical direction, because this equation can be used whenever there is uniformly accelerated motion, else we cannot use these equations. So when we have thrown the particle horizontally, their initial velocity in the y direction is 0, and the time taken to cross this x length of the plate is x by Vx, and the acceleration equation that we have already obtained. Now putting all the data here, uy is 0, so whole term becomes 0. So half acceleration is QE by m, and t square is x square by Vx square. So here for all the particle 1 by 2 is same, electric field is same, all the particle has to cover equal distance x in the horizontal direction, right, with the same horizontal velocity Vx. So again x square and Vx square terms are same for all the particle. The difference is their charge and mass, right. Their charges are different, that's why they have deflected by different angles in different directions. So here the deflection y is proportional to charge to mass ratio. It means the particle having large charge to mass ratio or highest charge to mass ratio will get deflected more, right. So here we can see from the figure clearly that the particle 3 has highest charge to mass ratio. In your book you can put scale in straight line, you can measure this, right. So for particle 3 it is highest. So the particle 3 has highest charge to mass ratio because it has highest deflection y. Question number 1.14. Consider a uniform electric field 3 into 10 raised to 3 I cap Newton per Coulomb. What is the electric flux through this field? Through a square 10 centimeter on a side whose plane is parallel to YZ plane. So as per the question, you can see there is a square, right, who is in YZ plane, right. This is Z and this is Y, so it is lying in that, and this electric field is crossing it perpendicularly, means the electric field is parallel to the area vector. So if you have any area like this or a circular, whatever the shape, the area vector always points perpendicular to it. So here the electric field is parallel to this area vector, so the angle between them is 0. So electric field is given in the question 3 into 10 raised to 3. Area is the side, one side of the square is 0.1 meter, it is 10 centimeter. so area becomes 0.1 into 0.1, cos 0 is 1. So if you solve this, you will get this answer, which is 30 into 30 Newton meter square per coulomb. Now in the second part of the question, it is said that it is what is the flux through the same square if the normal to its plane makes angle 60 degree with the x-axis. Means what you are doing, you are tilting the square, right? So you are tilting the square such that its area vector makes an angle 60 with the x-axis. That is, you are tilting square like this, right, such that its area vector makes an angle 60 with the x-axis. So it is EA cos 60. Now instead of cos theta, cos 0, we are using cos 60, and cos 60 is 1 by 2. So this expression become half. So it is 30 by 2, it is 15 Newton meter square per coulomb. Question number 1.15. What is the net flux of the uniform electric field of exercise 1.14? Means we have to use the data of the above question. Through a cube of side 20 centimeter, oriented so that its faces are parallel to the coordinate planes. Means that square is converted into a cube whose side length is 20 centimeter. So here we have a cube whose one side is 20 centimeter long, but it is placed in uniform electric field, right? So this calculation that I have done is only for uniform electric field. For non-uniform, we have to use a little bit different calculation. Now here I have labeled some surfaces. So the surface, right, this surface, the above surface, the uppermost surface, I have labeled as 1. It's your choice, you can label as you wish. The next surface that I have labeled this surface number 2, then this bottom surface is surface number 3, then the surface, this is the first surface which is touching the surface that I have labeled as surface number 4. The surface which is towards our side, this one, it is 5, and the surface towards the other side is 6. Now what is the expression for the electric flux? It is EA cos theta. So just compare the equation with the side. So for the first side, this one, the uppermost side, for the first side, this uppermost side, right, is the area vector is upward. Here you can see the area vector is pointing upward, and the electric field is in this direction. The angle is 90. So EA cos 90, it is 0. For the second surface, the second surface is labeled as this one. This is the second surface, right? For the second surface, the electric field and the area vector are pointing in the same direction. So it is EA cos 0. Cos 0 is 1, so it is EA. Third surface, which is the surface at the bottom. So at the bottom you can see here, right, this surface which is at the bottom, right, its area vector is pointing downward, right, which is labeled here. This is the area vector which is pointing downward here, right, and the electric field is in this direction. So it is again 90. So EA cos 90, right, again cos 90 is 0. Then the fourth surface, this one, which touches the electric field first. So for that surface, the area vector, right, let me label properly this one, right, this surface. So for that surface, the area vector is going like this, and the electric field is entering. So it is EA cos 180, because the electric field is entering the surface like this and the area vector is outward. So angle is 180. So it is EA cos 180. So cos 180 is minus 1. So it is minus EA. Surface number 5. The surface number 5 is the surface which we are facing, right? So that for that surface number 5, the area vector is outward and the electric field is in this direction. So again the angle is 90, and similar for the surface number 6, which is on the other side. So if you add all this flux, the net flux you will get is 0. So a little bit hint I am giving you, whenever there is any surface of any shape, but there should be a 3D surface, like a sphere or like a cube, 3D surface, any shape or size, but the surface should be 3D. If it is placed in uniform field, keep in mind, if it is placed in uniform field, then the net flux is always 0. Question number 1.16. Careful measurement of the electric field at the surface of a black box indicates that the net outward flux through the surface of the box is, so flux is given. It is asked what is the net charge inside the box. So we know that flux using Gauss law, it is Q by epsilon naught. So if we want Q, then we can make Q as a subject, it is phi into epsilon naught. So the value of phi, which is given 8 into 10 raised to 3, and the value of epsilon naught is 8.854 into 10 raised to minus 12. If you multiply, you will get 70.8 into 10 raised to minus 9, or you can just round it off as 7 into 10 raised to minus 8, or you can just bring 2 digit down, right? You will get 0.07 microcoulomb. Now in the B part, it is a very easy question, right? In the B part of the question, it is asked that if the net outward flux through the surface of the box were 0, means suppose there is a box, right? Let me draw a box for you, right? Let us assume there is a box. So let us assume this is a box. I am not drawing cube, but you can imagine, right? So this is a box, right? And from this box or this cube, the net flux coming out is 0. So it is asked that can you conclude that there is a charge or not? If you conclude yes, why? If you cannot conclude, why? See, let us assume there is no charge. Condition number 1, right? Q net, the Q is equals to 0. There is no charge, not a single charge. Let us assume I am making two situations. In the first situation, not a single charge inside it. In that case, net flux is 0. Condition number 2, there is a charge. Let us assume there is a dipole. One is positive, one is negative. So there is a dipole. Now in the second case, there is a dipole inside the cube. Means the net charge is also 0. So here charge is present inside the box, but the sum of charge is 0. So in this case also the net flux through the box is also 0. So we cannot conclude whether the charge is present inside the box or not, but we can only conclude that net charge is 0, but we cannot conclude that there is no single charge present in the box. Question number 1.17. A point charge plus 10 microcoulomb is at a distance 5 centimeter, which is shown here, right? Above the center of a square. So that square I have drawn here. So in this square you can see there is a charge which is lying above it 5 centimeter. What is the magnitude of the electric flux through the square? See, whenever we want to use Gauss law to find the flux, we need 3D surface, right? Without 3D surface you cannot apply Gauss law. So what I have done, here it is given one square. So I am making a cubic Gaussian surface. See, Gaussian surface I can choose by myself. It's my choice, right? So what I have done, I have made a cube such that, right, the charge now inside a imaginary cube. It is actually above. It is not actually inside a cube. It is actually above a square, right? Here you can see there is a square. The charge is actually above this square. But what I have done, I have made an imaginary cube over it. So now the charge is exactly in the center of this imaginary cube. So for a Gauss, if we apply Gauss law, then from Gauss law it is flux is equals to Q by epsilon naught. And here the charge Q should enclose in the 3D surface, that is a Gaussian surface, right? So if this square is a part of this cube, if the square is a part of this cube, then how much flux will come out of it? Q by epsilon naught from this cube. But now this flux is divided between 6 surfaces, right? It is divided between 6 surfaces, right? That already we have done in the previous question. So this flux is divided between 6 surfaces. So the flux through the single cube is Q by epsilon naught, but flux through each surface is divided by 6. So your final answer will be, so the charge is given 10 microcoulomb, 6, and here the value of epsilon naught. If you solve this, you will get 1.88 into 10 raised to 5 Newton meter square per coulomb. 1.18. A point charge of 2 microcoulomb is at the center of a cubic Gaussian surface of 9 centimeter age. What is the net flux? Again, it's a very easy question. Flux is equals to Q by epsilon naught. Just put the value of Q and epsilon naught. So Q is given 2 microcoulomb, epsilon naught is 8.85 10 raised to minus 12. You can solve, you will get 2.25 into 10 raised to 5 Newton meter square per coulomb. Number 1.19. A point charge causes an electric flux. So here flux is given and it is negative. Whenever the negative flux is given, it means the field is entering the surface, entering the imaginary surface, right? To pass through a spherical Gaussian surface of 10 centimeter radius. So here I have drawn, you can see this surface, the first surface is of 10 centimeter radius. If the Gaussian surface were doubled, how much flux would pass through the surface? Means if you double, means is 10 centimeter radius was there. Now I am doubling its radius. So now it becomes 20 centimeter. So now this is our surface, right? So what will happen to the flux? See, flux, if let us assume I have charge Q here, let us assume this is charge Q. If I am drawing this surface, in this case the flux is Q by epsilon naught. If I am increasing the size, again the flux will remain same. So the flux does not depend on the shape and size of the surface. It only depends upon the charge enclosed in the surface, not the size of the surface. So the flux will remain as it is. So flux does not depend on the geometry of the surface enclosing the charge. So the flux will remain same as it is given. What is the value of the point charge? So value of point charge is asked. Now we know Gauss law, flux is equals to Q by epsilon naught. So Q is equals to 5 into epsilon naught. So just put the value, you will get your answer. Now question number 1.20. A conducting sphere of radius 10 centimeter has a unknown charge, right? If the electric field 20 centimeter from the center of the sphere is, see, it's a very easy question. What is given? We have a conducting sphere of radius 10 centimeter. So let us assume this is a conducting sphere whose radius is 10 centimeter. Now for a conducting sphere, the charge will not remain inside the sphere. No electric field will penetrate the surface, right? So the net charge and the electric flux, electric field, not flux, net charge and the electric field inside this sphere is always 0 because it is a conducting sphere, right? Now it is given that at 20 centimeter from the sphere the electric field is given, right? Then it is asked that, and which is pointing radially inward, means if it is pointing radially inward means a negative charge is enclosed by the surface. Then what is the net charge? It is asked what is net charge. Now in the question it is given electric field is given 1.5 into 10 raised to 3 Newton per coulomb. So what is the equation for the electric field due to a point charge at a distance r is kq by r square. So kq by r square. So if I make q as a subject, it is ar square by q, er square by q. So e then r. R is the distance of a point from the center. Although the charge is on the surface, but the center of the charge is here. So instead of imagining charge on the surface, we imagine that the charge is located at the center. So the center is located at 20 centimeter from this point, right, which is lying on an imaginary sphere or Gaussian surface of radius 20 centimeter. So I am making q as a subject. So value of k is 9 into 10 raised to 9, value of r is 20 centimeter, which is 0.2. If you just put the data and solve, you will get 6.67 into 10 raised to minus 9 coulomb, which is 6.67 nano coulomb. A uniformly charged conducting sphere of 2.4 meter diameter has a surface charge density. It is also uniform, right? So surface charge density is given. Find the charge on the sphere. We have to find charge. Now how I will find charge? We know that the equation for the surface charge density is sigma is equals to q by epsilon naught. So q equals to sigma into A. Sigma is given, area is given. So sigma into 4 pi r square, and the radius is given. See, the diameter is given 2.4 meter, means the radius is 1.2. So the charge is 1446.9 into 10 raised to minus 6. Just shifting the point, we will get 1.44 10 raised to minus 3 coulomb. Now in the second part of the question, what is the total flux leaving the surface? Total flux means flux is equals to q by epsilon naught. So charge we have obtained, the same charge we put here, and the value of epsilon naught. We are getting 1.63 into 10 raised to 8 Newton meter square per coulomb. So it's a very question number 1.22. An infinite line charge produces a field 9 into 10 raised to 4 Newton per coulomb at a distance 2 centimeter. Calculate the linear charge density. So here we have this infinite long rod, right? It is infinite. Okay, so for infinite long, we know that the electric field is given by lambda by 2 pi r epsilon naught. So if I multiply here 2 and here 2, we will get 2k lambda by r. So it's a very general expression, right? There is no rocket science. So I am using this expression which will make my mathematics easy. So it is 2k lambda by r. Now make lambda as a subject, you will get, just I am shifting the term, so r will be this side, right? So it is E into r by 2k. Now the now electric field is given 9 into 10 raised to 4 electric field is given, and r is given. R is the distance where this charge is placed. So it is 2 into 10 raised to minus 2. Here it is 2, it is there, and the value of k. Now just by putting these values and calculating, we will get 10 raised to minus 7 coulomb per meter, which is actually 0.1 microcoulomb per meter, which is a linear charge density. Now last question of this chapter, question number 1.13. Two large thin metal plates are parallel and close to each other. So their inner faces question number 1.23. Two large thin metal plates parallel and close to each other. So which is given here, two plates, right, which are close to each other. On their inner faces, the plates have surface charge densities of opposite sign. So one is positively charged, another is negatively charged, and the density is given 17 into 10 raised to minus 22 coulomb per meter square. What is E? So we have to find electric field at three different places, right? One in the outer region of the first plate, in the outer region of the second plate, and between the plates. So here see, this is a topic of the textbook, right? So if we locate here, see, the electric field due to a plate is given by E is equals to sigma by 2 epsilon naught due to a single plate. So it does not depend on the distance, right? It is uniform. So at this place, the positive plate will produce field away from it, and this negative plate will produce field towards it. So both field are equal and opposite, so they cancel each other. So the net field towards the left is 0. Similarly towards right, this negative plate will pull, whereas the positive plate will push the field, that is the field is away from the plate. So as the field is equal and opposite, here I have calculated sigma by 2 epsilon naught minus sigma by 2 epsilon naught. It does not depend on the distance, right? So the net field again 0. So at both this place, the net field is 0. If we try to check between the plates, this is true only if the plates are oppositely charged, right? If they are same, both are positive or both are negative, then our answer will reverse. Okay, so here in the between, the positive plate will produce field towards right, and the negative will also produce towards right. So their field will get aided, sigma by 2 epsilon naught, sigma by 2 epsilon naught, right here. and it becomes sigma by epsilon naught. Sigma by 2 epsilon naught plus sigma by 2 epsilon naught, it becomes sigma by epsilon naught. So now we have sigma and epsilon naught, we can directly calculate it, right? So in the outer surface it becomes 0, no need to write whole calculation, just you can write this much. Similarly on the second outer region of the second plate, again it is 0, that we have already discussed, and between the plate it is sigma by 2 epsilon naught plus sigma by 2 epsilon naught, it is sigma by epsilon naught. Sigma is given 17 into 10 raised to minus 22, epsilon naught we know this value, if you solve this you will get 1.92 10 raised to minus 10 Newton per Coulomb.